for the FDP today. Professor Y.K. Vijay received his MSc degree in physics and PhD degree from University of Rajasthan, Jaipur in 1975 and 1980, respectively. He was awarded Commonwealth and ICTP Fellowship and spent 1 year in Uppsala University, Sweden. He served as a professor, Department of Physics, Director, Center for Development of Physics Education, and Center for Non-Conventional Energy Resources at University of Rajasthan, Jaipur. Over 250 research articles in referred journals, citations over 3000 H index 30, and over 150 research papers in conference proceedings. He has delivered over 100 invited talks and has co-authored 2 books on basic and semiconductor physics. He has graduated 40 PhDs and advised numerous masters and undergraduate research projects to date. His professional awards include IUMRS Young Research, R.K. Ramnath, IAPT Teaching Aids Award. He has also developed electron-positron accelerator, XRF CVD, and positron lifetime spectrometer. He has spent 38 years in teaching and research field of semiconductor, thin films, and nanoporous polymeric filters. His current research interests are polymer blends for organic photovoltaic cells, design and development of CNT polymer composite-based gas sensors and gas separation filters. He is also studying photoluminescence and non-linear optical properties of nanoparticles, doped polymeric composites. He is life member of IAPT, APS, NSI, IPA, RAPT, MRSI, and president of IAPT RC6, as well as Rajasthan chapter of MRSI. Here he will enlighten us with quantum science in visual range, where he will be able to visualize some complicated quantum phenomena of physics with ease and will get benefited in long run. Thank you.
Thank you.
Thank you, sir. Now I'd like to call our Honorable Vice Chancellor, sir, for a special address to the participants.
स्वप्ना मैडम को क्या दिखा रहे हो म्यूट कर
everyone here today. My sincere thanks to Professor Y.K. Vijay, who is with here today, who has given his kind consent to be with us and deliver a special talk on quantum science in visible range. Professor Vijay has already been introduced to you by a distinguished faculty member, but the point is that to describe his achievements would be showing a small diya to a Surya. Surya ko Deepak dikhane jaisa hoga. Professor Vijay has a distinguished career and illustrious academic and research career throughout his life till now. He has a passion for academics, and that is amply reflected in the introduction which has been given about him. Sir, we are privileged to have you with us today, and I am sure that when you talk about quantum science in visible range and explain the basics and details of quantum physics to the participants here, it would be a great learning for all of us. I am very thankful to the Dean Academics of Pratap University, Dr. Shanmugam, the HOD of the School of Basic and Applied Sciences, Mr. Ramayana Singh Chauhanji, and the FDP Coordinator, Mr. Gaurav Sharma, for having been able to request Professor Vijay to be with us today. Thank you so much, sir. I hand over the proceedings to you. Thank you so much.
Thank you, sir. So now you can start, sir, your session, sir. Thank you, sir.
Okay, thank you so much. I like to share my screen. So somebody has to activate. Please share my screen to the audience. Yes. Thank you. Good morning to you all. Well, as I'm thankful to the Vice Chancellor Pratap University and the management committee who has taken a decision that they are ready to listen to me, what I say. And I, in fact, chose a very interesting topic for young students, that they learn the quantum physics or quantum science, but they never appreciate in this world the importance of these small particle and their dynamics, their interaction is responsible for most of the phenomena in the universe. So I would share most of the quantum phenomena which they learn in different courses through laboratory experiments, which we have designed and developed during my tenure from University of Rajasthan, and then Vivekanand Global University, and now at the Center for Innovation in Science Teaching, CIST, at IIS University, Jaipur. This is my email address for the students. They can contact me, and this is my website, Google homepage, Vijay YK. They can visit and find details about most of these experiments which we have designed and developed. So, well, this is a brief introduction about the topics I will be covering during my presentation of 45 minutes or so, and then I will take up few discussion point of view or queries if they are there. In fact, in nature, we come across atoms and molecules, okay? And that is what constitute every material. Even the solid mass has got atoms, liquid has got mobile atom, and vapors or the gas has got really dynamic atoms and molecules. And that is how we look at our Mother Earth, that there are three form of material: liquid, solid, and gases. And they are composed of these tiny atoms and molecules. And how do they interact within material? That is what we like to appreciate. And most of the phenomena which we find in our nature and in the chemistry or in the physics or in the engineering, they are all responsible because of these atomic interaction. So let me have a first theme as atomic configuration, how the atom interact. They interact through van der Waals interaction. So this model has got these balls, okay, plastic balls, and they are floating on the surface of water. What I have done is I have mounted a ring magnet on each one, okay, so that they don't touch each other. And this is what happens normally in material. Most of their atoms, they are far apart. They don't touch each other. That we don't know. Okay. And if you want to see the behavior, let us see the video.
In order to show atomic configuration, we have got a model in which the ring magnet is attached on each ball with identical polarity of north-south, so that the dipoles are interacting. The balls are able to float on a surface of water, and they arrange themselves in a particular configuration. 7 ball with hexagon symmetry, 5 ball or 6 ball with pentagon symmetry, and when there are 4, they result into a cubic symmetry. If there are only 3 balls, they are having a triangular configuration. So the atomic configuration is also similar to the spherical atoms, having interaction, van der Waals interaction, and organize themselves in different pattern when they are repelling each other.
So ultimately, a solid is an aggregate of different atoms. And if you want to model it out, how the atoms are arranged, okay, these are the tiny balls which are fitted between 2 parallel plates. That is what we call it as atomic model. And here they are arranged very nicely. We call it as a hexagon close pack structure. And here they are arranged in a cubic fashion. But here they are arranged with some gap. We call it as a dislocation. Here one ball is missing. We call it as a vacancy. And you see this region all around. We call it as a grain boundary. This is also a grain boundary. So most of these solids, when atoms are packed, they don't touch. Okay, this is a model which is showing a close contact, but in nature, they don't touch. They are far away because of the van der Waals interaction. If you press them, they come close. As you release them, they go away. They are far apart. Okay, even in liquids, atoms are not touching. Even in gases, the atoms are not touching. Let us see the dynamic of this model, how it looks like.
We have a model for solid in 2 dimensions where the spherical ball of steel are about 10,000 in number, placed between 2 parallel plates having a spacing around 1 mm. And when we see through, then we see the dense random packing of hard spheres as a model with a lot of defects in it. The grain boundaries, the vacancies and dislocation are visible throughout the structure. So the solid, it shows a plane, a monatomic plane.
Normally, to look through the solid, you need sophisticated technique like X-ray diffraction and the transmission electron microscopy or scanning electron microscopy that is used for visualizing the surfaces. Okay, but fundamentally, the interaction of atom is through the van der Waals force. We call it as a van der Waals interaction. And the van der Waals interaction is having the 2 kind of forces. One is force of repulsion, okay, and another is force of attraction. And the combined effect result into some sort of an equilibrium position beyond which the particles are kept apart. So because of the positive nuclei, they don't collapse. And because of the electron cloud, they don't come close, very close, and they don't go far away. And that is what we call it as an exchange force. Okay, so there is a force of attraction as well as force of repulsion, all right, between any 2 atoms. That is what is the fundamental. In order to represent this, we have got this model. in which we have got a bar pendulum, which normally works because of the gravity, and the repulsion is introduced using these magnets, permanent magnet. One magnet is here, another magnet is here. So when this bar pendulum is suspended, okay, how it comes in the equilibrium, just have a look. I have got this video.
We have a small bar pendulum in which there is a gravitational force of attraction at the center, but there is a repulsive force of magnetic interaction that results into a van der Waals configuration, and it comes in equilibrium at certain distance. When you release it, it never comes to the center.
Because of the identical pole repel each other. And that is what happens in nature also. Positive charges at the nucleus, they don't allow the atom to come close. Okay. Let me have these two atomic configuration like a molecule, and how the electron dynamics takes place within the molecule using such a model.
Van der Waals potential is found in crystals. In order to represent that, we have an oscillating magnet between two permanent magnets. So sometimes it finds the kinetic energy is not enough to cross the potential barrier, then it is trapped close to one of the magnets. It can be trapped in a magnet, one magnet or another magnet. Okay, shows a bound electron, and once it has enough energy, it shows a continuous.
So if the electrons are localized, we call them as a bound electron. If the electrons are free to move within the solid, we call them as a conduction electron, and that is what is the normal solid structure. Let me explain another phenomena which is very important here, is an anharmonic oscillator. Normally, we say that atomic systems are harmonic oscillators, but they are not, because they are having a non-linear restoring force. You see, the harmonic oscillator is only one when the restoring force is given by this equation, F is equal to minus kx. Okay, spring mass system is a harmonic oscillator. Simple pendulum is a harmonic oscillator in a limited amplitude. But when the amplitude is large or spring becomes nonlinear, then you have such a situation. Okay.
We have modified a bar pendulum in which the restoring force is due to gravity as well as the magnetic interaction. At the bottom of the bar, we have a magnet oscillating with respect to a fixed magnet on the table. The resultant motion is that it is an anharmonic oscillator, because the restoring force
has got two terms now, the magnetic interaction and the gravitational interaction. The sign is also, one is negative, another is positive. Okay, the identical poles, they repel, then the gravity brings it at the center. This point, the gravity brings it down and the magnetic interaction is pushing it away. And now it is having oscillation in a particular plane. So this arrangement, we call it as an anharmonic oscillator. Let me illustrate it again using this model with magnetic attraction at the center in place of repulsion, so that the gravity and the magnetic interaction, they are both together. And see the dynamics.
In this model, we have got a bar pendulum with strong attractive magnetic interaction at the bottom. Shows a very good character of a harmonic oscillator. When the amplitude of oscillation is large, the time period is also large, but as the amplitude reduces, the time period also decreases very rapidly. It shows anharmonic oscillator potential. It's basically the magnetic interaction dominantly and a little bit gravitational interaction. Both are having the same direction towards the center. This is analogous to the bound electrons are having a very high energy close to the nucleus, while those who are having far away, they are weakly bound.
So this shows the potential well across the nucleus.
In this model, we have got a bar pendulum.
So now if I say that these oscillators show the fundamental phenomena of vibration, oscillation, and energy exchange, okay? So Raman effect was the very fundamental phenomena described by C.V. Raman. Can we illustrate this phenomena of interaction of photon with atom? Okay, this is what C.V. Raman explained, that when photon interacts with atom, sometimes the energy of the photon increases, sometimes the energy of the photon decreases. And that's how it exchanges energy with the electron. And electrons are having different energy levels within the atom. So these are different energy levels. So this is analogous to an atom, which has got independent frequency, and this is like a photon, but they are interacting through magnetic interaction. And this magnetic interaction is sometimes in phase, sometimes out of phase. Once it is in phase, then the energy of the photon increases, and if it is out of phase, then the energy of the photon decreases. And that is analogous to Stokes and anti-Stokes line in Raman scattering. Okay, so what I mean is that the fundamental quantum phenomena we can explain using such mechanical models, and at the same time they illustrate the fundamental science. For example, the Bohr orbital. Bohr orbital, everybody knows that the electron around the nucleus moves in a circular orbit, and the Bohr quantization rule says that when 2 pi r, the circumference of this loop, okay, is equal to integer multiple of lambda, then we have the stationary states. So this can be found in this sort of setup. So this is again a speaker. On a speaker, a loop, flexible loop is mounted, glued, and the speaker is connected to a signal generator so that we can introduce vibration here. And these vibrations travel in this loop in a clockwise or anti-clockwise direction that results into stationary waves. So these stationary waves within the loop, okay, they result into this sort of a node and antinode. These are the antinodes and these are the node points, okay? And the separation between the node and antinode is equal to the lambda. So this is a situation of a 3 lambda, all right? So there are 3 waves in a circle, okay? There could be 2 waves or 1 wave depending upon what is the frequency here, okay? Because frequency is connected with the wavelength here. In electron dynamics, as the energy changes, the orbital size changes, n equal to 1, n equal to 2, and n equal to 3. So these are different energy levels across the nucleus. So when you want to see the dynamic form, this is how it looks like. When you adjust the frequency, then you get antinode, node, antinode, node, and antinode, and you can count the number n, and 2 pi r is fixed. So what you do is you vary the frequency, you get different stationary state of oscillation of this loop, analogous to the stationary state predicted by Bohr orbit. This Bohr orbitals can be demonstrated again using such a mechanical setup. Okay, so here you can really see that this is the vibration frequency, and this thread is connected to this loop. Okay, this is a floating loop, and the energy is transferred here. The energy travels clockwise or anti-clockwise. They form the stationary waves in this loop and result into the same situation when 2 pi r equal to n lambda. N is the frequency here. So this is in the really low frequency range, around 0.5 hertz, and the other one works in the higher frequency range, around 20 to 100 hertz. Okay. In atom, the frequency is much higher. Okay. Sometimes in hydrogen atom, the frequency goes to something like terahertz. Okay. The Balmer line or Paschen line, that is what we study in the hydrogen spectrum. And here I illustrate the frictionless track, and the friction is because of the two surfaces having contact. Okay, when you have two surfaces and rubbing, the atomic interaction is there, and that causes the friction. So if you have some air cushion in between, then there will be no contact between these two surfaces, and it may result into frictionless motion. Let's see through this video. This is a glider which can move on this tube, blowing air through a blower, air blower. And this is how it looks like. You see there are magnets, identical pole, so they are repelling. So normally the atoms collide, but they don't touch, okay, because of the van der Waals interaction. This is a model, okay. This is how the collision takes place and the interaction is there. So this is another modified version of this to illustrate the but here between these two magnets, this is like a nuclear potential valve. It passes through if the energy is more, okay, and the potential well is oscillating, so there is interaction. And if this interaction is in phase, okay, then it gives a kick to the alpha particle, and if it is out of phase, then it absorbs the alpha particle, capture. Again it escapes. Escapes again. Escapes. Now it is trapped and then escapes. Okay, so this magnet, oscillating magnet, gives a partial kick, although it is trapped, but knocks out like alpha decay. All right, next time it may be trapped or it escapes. It escapes. Okay, so these are all basically the mechanical model. All right, I have another set of mechanical model to show the another quantum phenomena of molecular vibration. For example, this water molecule, Water molecule consists of oxygen and hydrogen. Okay, and they are attached with some van der Waals force. So this is a mechanical model. So it has got a spring mass system. Okay, when we vibrate, this is how it vibrates. Okay, because it picks up energy from the speaker, and we can tune the frequency. Okay, and if you tune another frequency, then it vibrates this way. So this is called mode of vibration. When you change the frequency, the molecule can absorb energy in this mode or this mode. Okay. In the same way, this is a methane molecule, analogous to methane molecule, CH4, where you have the carbon and the hydrogen, 4 hydrogen, and they are at 109 degrees each. Okay. When you excite, you see, all of them are vibrating in a zigzag way. We call it as a torsional mode of vibration. Okay. But as we change the frequency, there is another resonance frequency. When these are vibrating up and down, we call it as a stretching mode of vibration. So the methane molecule can be excited with the torsional mode as well as the stretching mode. And that's how they are described in the literature. Let me explain you the Rutherford scattering phenomena. You know, the Rutherford scattering phenomena is a very fundamental, because most of the nucleus is positively charged, and when alpha particle is hitting this positively charged nucleus, it gets scattered, and that's how you get idea about the size of the nucleus, and that is what Rutherford explored. Okay, and the size of the nucleus is of the order of 1 Fermi or 2 Fermi or 3 Fermi. Okay, depending upon how many nucleons are there. In heavy nuclei are bigger, lighter nuclei are smaller in size. So this phenomena, in order to see in the laboratory, what we have is a magnetic ring, and this is a magnet again. Okay, when we release this magnet, how far it goes and goes in a particular direction. So angle of scattering we can measure. Okay, this is how it works. This is all mechanical modeling. Okay, we can vary the kinetic energy, displace it with different amplitude. Okay, we can change the angle or the impact parameter by placing this ring magnet at different position. And on the dial, we can measure the scattering angle. Okay, so all these apparatus are designed, developed innovatively to learn the fundamental science, but the fundamental science to bring in the visible range. Because Rutherford scattering phenomena, you cannot see where the alpha particle is going. Okay, how do you see it? Okay, the trajectory we cannot. So it's only the calculation based, and then on statistical analysis, we predict about the size of the nucleus. Okay, and here these are all mechanical model based. Let me explain you another very interesting phenomena, which is called the plasma, or the fourth state of matter. Okay, in atmosphere we have got air, which is mixture of nitrogen, oxygen, and carbon dioxide and other gases. Okay, and the density of air is about 10⁻20 molecules per cc. It's a very large number. They follow the kinetic theory of gases, and they move randomly. Most of the molecules move randomly. They are compressible, but if in a closed chamber, which is airtight, using such O-rings, okay, and with a small tube, you can remove the air. So inside this chamber, you have air with the low pressure. Low pressure means the number of molecules are reduced, because some of them you suck out and this is what we call it as a vacuum. Okay, so when the gas is at low pressure, all right, then you can excite these atoms, okay, and ionize them. All right, if you excite and ionize them, then this is called the ionized state of matter, and ionized state of matter is called plasma. Okay, and in the plasma you have got ions, positively charged, and the electrons, which are negatively charged. They are coming from these neutral atom. So gas is neutral normally, but if you reduce the pressure and apply some voltage, then you can ionize them. And once you ionize them, they recombine also. The positively ion and the negatively charged electron, they recombine because of the collision. And once they recombine, they liberate light. So let me show you the experimental video. This is how when the vacuum pump starts. And we have applied some biasing across these two electrodes. These two electrodes, one is positively charged and another is negatively charged. High voltage is applied, and when the critical low pressure is generated, suddenly because of this voltage, the gas discharge takes place, and because of the gas discharge, conduction, some positively charged and negatively charged ions are separated. So negatively charged are basically the electron, okay, they go to the positive electrode, and the positively charged ion, they come to the negative electrode, and therefore the light is more here and less, okay. And you can find
we have a small vacuum chamber about 2 liters, in which we have got 3 electrodes where we can apply some biasing. And to the electrode,
700 volt we have to apply.
one straight wire is connected of iron, and another a ring electrode is connected. Once there is air, there is no flow of current when biasing is there. When we remove air, suddenly the gas discharge starts, and we get a very nice plasma across the electrodes. Across the negative electrode, where the ions are collected, we get more density of the plasma. Across the positive electrode, where the electrons are collected, there is no much illumination.
So, well, what I have done is we have developed several innovative experiments and apparatus to illustrate fundamental concepts which are useful for understanding and developing further, okay, for young science and engineering students. All these apparatus or the experiments, I say, are demonstrative. They demonstrate certain phenomena. They are quantitative. Quantitative measurements can be made, and easy to fabricate, okay, at low cost. So all of them can be fabricated or developed in any laboratory, okay, and many such models are developed, all right, and they basically teach student and teacher what is the concept, skill of making and developing innovative ideas. All right, if you design and develop something, then of course you can do some big science or rocket science. So you have to start with small projects, and if you can explain some phenomena using small projects, then certainly you can think of doing something great or something big in times to come. All right, until and unless your fundamentals are clear, Okay, you cannot develop big machines or big ideas or big experiments. Okay, and what I say is enjoy learning through playing. Until and unless you play with the things, you cannot learn. All right. So most of the experiments are available in the physical form. Okay, and you can play with them. You can change the parameter, you can change the amplitude, you can do the quantitative measurements, you can do a video recording. Okay, and learn the fundamental process of interaction. So in nature, what I like to say is that all globe has got three form of material: solid, liquid, and gas. And ultimately, every material is made of atoms and molecules. How do they interact? That is what is responsible for its state, like liquid, solid, and gas. Okay. Within solid also, all right, how do they arrange within the solid? That decides their resistance, their thermal conductivity, their specific heat, and so on. So various properties of the solid are connected with the atomic arrangement and the crystal structure and the impurities in it. Okay, like in semiconductors, the impurity changes the conductivity in a drastic way. All right. So in order to understand the fundamental of material science and engineering, we have to understand the interaction between the atoms and molecules. We call it quantum interaction or a quantum phenomena. Okay. And what we have done is illustrate all these quantum phenomena basically within the visible range. Okay. So what I described today, let me sum up. I described atomic configuration, van der Waals potential, Rutherford scattering, Bohr orbital, Raman effect, alpha decay, molecular vibration, and plasma state. Perhaps you will come across with these terms in your science and engineering projects somewhere, and try to remember the fundamental videos which I illustrated through this presentation. And if you want to see them again, you can visit the Google site, which I shared with you. It's my homepage, Vijay YK, on Google site. Okay. You search by the name YK Vijay, you will get the detail about the web page. This is how the web page looks like. Let me share with you. Okay, so you can visit that. All right. So let me sum up and stop sharing the screen. Okay, and ready to give answers to some of the questions if you have.
Thank you, sir.
Yes, sir.
Participant.
My presentation is over. Thank you. If there are questions, I can reply.
Yeah, FDP Cordinator.
Participant, you can write your question in chat box also.
Or you can send email, give your feedback. How did you like the concepts? And can you make use of these concepts in your studies further?
सर कुछ क्वेश्चन पूछ लो आप यूट्यूब पे हेलो सर हेलो सर
No, hello sir, can we use this to explain tunneling?
Well, in one of the presentation, I talked about this phenomena, like when you have this anharmonic oscillator, in anharmonic oscillator, when the energy is less, okay, then it doesn't penetrate the potential barrier. Okay, if the energy is more, then it penetrates. Okay, even in magnetic potential, well, on air track, you are having the phenomena of sort of a tunneling through the potential barrier. Okay.
Yes. And sir, in this alpha decay experiment, you showed
Yes.
that reflectance we can see. Like chances are less, but we can see the reflectance also.
Reflection from the potential barrier. Yes. So in alpha potential, if you change the polarity of the magnet, okay, the potential well polarity changes automatically. Right now it is attractive type, then it will be a repulsive type. Again, same oscillating. So these are the configuration which you can play with the apparatus. Okay, if you have this kind of setup. In fact, I should be happy to share with you that all these setup are available in the form of innovation hub, and within country we have set up such innovation hub at 20 different places. Okay, IIS University is one where we have the innovation hub right now, where my office is there, and at Vivekanand Global University, where we started developing these modules. We have set up the innovation hub. So that is available in Mathura. GLA University has got the whole setup. So all these models are available with them. Okay, they can be used by the students for demonstration purposes. Okay, we have installed this at Ajmer, Regional Institute of Education, Ajmer. We have installed at Bhubaneswar, Pune University, and Rahul Bajaj Science Foundation, Wardha. Okay, so these models are there for teaching and learning exercises. Okay, and most of these videos are available now on website. Okay, so you can design your own apparatus using these ideas and set up somewhere. Okay.
Thank you, sir.
Thank you, sir. Now I call our Deputy Registrar, sir, for the vote of thanks.
Okay, thank you.
Good afternoon to all.
Good afternoon.
As all good things come to an end, so is this faculty development program. On behalf of Pratap University, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this FDP on quantum science in visible range, organized by School of Basic and Applied Science. At the outset, I thank our resource person, Professor Y.K. Vijay. We are really enlightened with your knowledge and presence. We are thankful to our honorable founder, Mr. Ram Singh Bhadoria, and Chancellor, Mr. Shailen Bhadoria, for their motivation. I would like to thank our Vice Chancellor, Professor Dr. Abhay Kumar, for his enthusiastic support. I would like to thank Dr. M. Kandasan, Registrar, Pratap University, Dr. R. Shanmugam, Dean Academics, Pratap University, and also a special thanks to the organizing committee, Mr. Raman Singh Chauhan, Mr. Gaurav Sharma, Mr. Dheer Singh, Mr. Arvind. I thank to all teaching and non-teaching staff for their unflinching support and coordination. Our heartfelt thanks to our students for active participation. With these warm words and a kind message, we move to the end of today's faculty development program. Thank you so much.
Thank you.
Okay.